Okay, I want to thank all of you guys again for coming to our fall seminar, 2020 seminar series. We've had a good run. This is our 6th guest speaker. We've had some really good, at least I think so, interesting presentations. And this one is also very interesting and I think very important as well. We will, as we normally do, have a student present, do the introduction of our speaker. And this week, the student is Aaron Jacobs. And what I have here about Aaron is that he is currently a senior in our department, majoring in chemistry, ACS concentration. And he went to school, Roscommon High School in Michigan. Honestly, this is the first time I've heard about Roscommon. That is really interesting. Is that middle of the state, western part of the state? Where's the?
Yeah, it's in the north. It's like 15 minutes south of Camp Pasadena and Grayling.
Okay, okay, very good. So Aaron plans to get into graduate school. He would like to teach after some years. Hobbies include soccer, rock climbing, and also, yeah, I think I know about this, working at the summer camps. How many summer camps you've done since, yeah?
Well, so I've worked only at Camp Pasadena, but this coming summer will be my 5th year.
Yeah,
summer.
Yeah. That's a cool experience, man. So anyway, Aaron, do the honors of introducing our speaker for today.
Absolutely. And actually, speaking of camp, this is where I first met Dr. Crounse.
Okay.
He and his family were vacationing there. I was working at High Venture. So this is our 2nd time meeting, and he was telling me about his research. So I'm looking forward to getting the whole expose of what he does. So Dr. John D. Crounse, he grew up in southwestern Michigan, and he attended Andrews Academy and subsequently went to Andrews University and completed a bachelor's in chemistry and mathematics and earned a secondary education teaching certificate. After undergraduate studies, John worked for a time as an analytical chemist at LACO Corporation in St. Joseph, Michigan. Next, he moved to Southern California and started graduate work in the Division of Chemistry and Chemical Engineering at Caltech, focusing on studies of chemical reactions with the importance for the atmosphere and developing state-of-the-science instrumentation for quantifying multifunctional molecules. After completing a PhD in chemistry, John remained at Caltech as a research scientist, continuing studies of atmospheric oxidation mechanisms, instrument development, and making in situ observations of trace gases in the atmosphere from aircraft and ground-based platforms. And John enjoys spending time with his wife and his 3 kids and tinkering with electronics. So we're looking forward to this presentation and learning more about your research. And please join me in welcoming John Crounse.
Okay, well, thank you. Let me see if I can share this screen. Okay, let me know if for some reason you can't see that or my mouse pointer. I'll try to pay attention to the chat, but very likely we'll lose track of that. So if you have a question or if something's not going well, please just interrupt me and shout out, and that's the best way to get my attention. So today I'd like to talk to you about some of the work we've been doing at Caltech over the last, I don't know, 10 years or so, is when most of this has been done. And I hope that I can convince you that this is interesting and that maybe it even has importance for your day-to-day life. This picture is one of my favorites. It's from a tower-based experiment that we were part of in northern Michigan, right near Camp Pasadena, in Pellston. the University of Michigan has a forest research center there, and we were able to participate in an experiment in 2016. So this is from the top of their 20-meter tower where we had our equipment for a few weeks. I'm going to start off just with a couple acknowledgements in case time gets short at the end, and I don't want to forego that. On the screen, I'm showing pictures of two individuals who were very important mentors to me over my younger years. Cleon White was a teacher at Andrews Academy for a number of years. He taught chemistry and mathematics, and he was later the principal at Andrews Academy, and he's now retired. He really got me interested in chemistry, and is probably one of the main reasons why I pursued a career in this field. He recommended that I should apply for the Dow Chemical Scholarship, which really, I was fortunate to be able to study at Andrews using that funds from that scholarship. While at Andrews, Dr. David Alonso, who was a professor in the chemistry department for a number of years, he was my research advisor. I think I did research with him for probably 2.5 or 3 years, including some summer research and research during the academic years. And he was the first person who broke me into the field of doing scientific research. And I really appreciate his efforts in training me up, and hopefully in a manner that paid off, where I could do good scientific research. Here are the two faculty members that are still part of the Andrews University Chemistry Department, Dr. Nowak and Dr. Murray. I was fortunate to have classes from both of them while studying at Andrews, and I had organic chemistry from Dr. Murray and biochemistry from Dr. Nowak, and I really enjoyed the classes. In fact, I was able to have classes from all of these people, most of which are now not members of the chemistry department, and you can see what they looked like almost 2 decades ago, which is a little different probably than nowadays.
A little? Wow, look at that man, he has hair. Ryan Hayes, if you're listening, watch out. Time's coming after you.
Changes happen to everything. Time is sometimes not our friend. But I just wanted to say that I think the education that I got at Andrews University more than adequately prepared me for continuation on into higher levels of work, graduate work in chemistry, and that is really hard to do at a small private school. And so I really commend the chemistry department there. You guys do a great job, and I'm impressed every time I think about this. Okay. Oops. So moving now on to Caltech. I work with a research group there that is led by Professor Paul Wennberg. This is our group picture that was taken, I think, within the last year. So we have, about 10 to 15 different distribution of graduate students and postdoctoral scholars and staff scientists. And I work in the group as a staff scientist. The Wennberg group is divided into two main parts. One part that makes measurements, column measurements of trace gases in the atmosphere using FTIR spectroscopy. So they'll put a FTIR sensor on the ground and look at the sun, and they know what the solar spectra looks like above the ground, and then they measure the spectra at the ground. And so the difference between the top of the atmosphere and the ground level spectra contains information about the absorbing species in the column. And so they can extract column measurements of a number of trace gases using that technique. The second side of the lab, which I am the leader of, is the chemistry side. And we use mass spectrometry methods to measure trace gases in the atmosphere, reactive trace gases that tell us something about the chemistry that's going on. I won't talk about this stuff, but we do plenty of work in the field. We use our instrumentation from aircraft platforms. Pictured here is a DC-8 aircraft that NASA runs for atmospheric chemistry purposes. And they'll load up this full plane with different types of analytical instrumentations that can measure in real time the chemistry that's going on in the atmosphere. And here's a picture of our instrument inside the plane. We have 2 mass spectrometers that generally fly on the payload, and they measure things like organic acids and inorganic acids and peroxides in the atmosphere. We've also deployed our instrumentation on ground-based platforms. Usually these are on towers to try to get above the surface of the ground a little bit to better represent the boundary layer composition. So let me start off by giving just a little bit of background in atmospheric chemistry. So I like this schematic, even though there's many things going on there, because it gives you an idea of the wild nature of atmospheric chemistry. You can think of the atmosphere as a giant chemical reactor, and it's full of different chemical reactions. We have emissions processes where constituents are put into the atmosphere by both processes that are anthropogenic and by natural processes. And then these emissions, they become transformed because we have, of course, the sun, which is irradiating the atmosphere with photons during half of the day. And those photons are fairly energetic enough to break chemical bonds and to excite chemical bonds. And so that can promote chemical transformations in the atmosphere. And so you can convert the things that were emitted into other things, which then can be moved around by the atmospheric winds and affect the air quality or composition in places far from where the initial components were emitted. And there's also a deposition where the gases can deposit to the surfaces, the ocean or the land, and be removed from the atmosphere. So we think of the atmosphere generally as 3 different portions. One is the boundary layer. This is the layer closest to the surface that is generally well mixed during the daytime because of the heating of the surface by the sun sets up a convective stirring. And so the boundary layer is rapidly stirred during the daytime. The troposphere is then a fairly stable layer. It's warmest at the bottom and coldest at the top. So the mixing in the troposphere is substantially less. And then we have the stratosphere, where the temperature starts to increase as you go up again. And so the exchange of gas between the troposphere and the stratosphere is a substantially longer time scale. Different constituents can do different things at different places in the atmosphere. For instance, ozone in the stratosphere we think of it as our sunscreen. It absorbs the UV, a large fraction of the UV radiation, which otherwise would reach the surface and cause problems to life on the surface. In fact, problems that we've had recently are the ozone destruction, which we call the ozone holes, which is driven in large part by chlorofluorocarbons that we released to the atmosphere some 30, 40 years ago. Those photolize up in the stratosphere and catalyze the catalytic destruction of ozone, and thus allowing much more UV to reach the surface. This chemistry was largely figured out by a giant in the field of atmospheric chemistry, Mario Molina and Sherlyn Rowland. Sadly, we just lost Mario Molina yesterday. He passed away at the age of 77. But those 2 chemists received the Nobel Prize in 1994 or 5, I believe, for their work in figuring out the ozone destruction in the stratosphere. Ozone at the surface now is an opposite, and we consider it a pollutant. It is detrimental to life, including plants and people. It's an irritant for the lungs, and I'll discuss a little more about that later. So what do we strive to understand as atmospheric chemists? there's a number of items, of course, but I've highlighted two of the most important ones. One is, these are our current foci in our research, and that's the formation of tropospheric ozone, where it's considered a pollutant, and the other is particulate matter. Particulate matter is small particles of various substances that are present. They are emitted and they form in the lower atmosphere, and they are detrimental to human health and also have impacts for climate. Both of these processes are complex and very interesting, and so given their importance and the interesting chemistry, those are sorry, keeps areas that we tend to focus on as atmospheric chemists. Health effects that are associated with ozone exposure it can cause difficulty with breathing, shortness of breath, pain in breathing, cough, sore and scratchy throats, inflamed and damaged airwaves, aggravated lung diseases such as asthma and emphysema, chronic bronchitis. You can have a correlated increase in frequency of asthma attacks. They make the lungs more susceptible to infections from other things. And it continues to damage the lungs even when the symptoms have disappeared. Ozone is correlated with chronic obstructive pulmonary disease as well. Aerosols, here's just a scale for how you should think of aerosol size. In terms of health and air quality, we tend to categorize particles into a couple different categories. PM 2.5 is particles with an average diameter less than 2.5 microns. PM 10 is somewhat bigger particles, less than 10 microns in diameter. PM 10 is often composed of dust, pollen, and mold, these larger things that make it into the atmosphere, whereas PM 2.5 are small particles that come from combustion, and they're also formed within the atmosphere by secondary chemistry of gas phase precursors. These have a small enough size, they can penetrate deep into the lungs and thus cause different health effects. So here's just an overview of particulate matter. The sources include direct emission, formation from in situ gas phase chemistry. So this is the interface of the things that I work on, which is mostly gas phase, with how particulate matter is formed in the atmosphere. Also, biomass burning is an important source of particulate matter to the atmosphere. So this is from a paper that was roughly a decade ago, published in Science, that shows you the composition of particulate matter around the globe. And the thing I want to point out here is that most of this organic matter is well, 50% or so is of the particulate matter is organic material. And then, you know, slightly less is inorganic. Of course, it varies from place to place. But a major component is organic. And most of the organic matter, which are these things in the green colors, are formed within the atmosphere. Those are due to gas phase chemistry from gas phase precursors, which then condense onto the particles, as opposed to things in the gray and the brown colors are direct emissions. So health effects with PM exposure include premature death in people with heart or lung disease, non-fatal heart attacks, irregular heartbeat, aggravated asthma, decreased lung function, lung cancer, developmental issues, increased respiratory symptoms such as irritation in the airways and coughing or breathing or difficulty in breathing. And here you can sort of see how far into the human body that different sized particles can reach. Most of the bigger stuff is stopped in the sinus area and the upper throat region, whereas the smaller particles can get down deep into the lungs, and even the smallest ones can even go through the blood barrier within the lungs and get into the bloodstream and move around the body that way. Just a PSA, since we're talking about aerosols, and given the situation that we're in with the spread of COVID, there's an abundance of evidence nowadays, now this year, that this disease is spread in the large fraction by airborne transmission, which is transmission with these smaller particles between 100 and 10, even 1 micron in diameter. These particles are small enough to be considered aerosols, and that means they remain in the air for long periods of time. They can remain in the air, airborne for hours as they ride the just the thermal eddies within an environment. And so it takes a long time for the air to lose these particles because sedimentation is very slow. So when people are indoors, it's really important to wear a mask, which can decrease the risk of contracting this from this airborne transmission rate. Increases in ventilation and filtration will certainly help remove these particles from the air. MERV 13 filters are good enough to remove predominance of these aerosol particles. And there's a recent write-up on this in Science by Kimberly Prather and other colleagues of ours at UC San Diego. Okay, so now back to some chemistry. Tropospheric ozone and particulate matter. The formation is often called photochemical smog. The understanding of this chemistry was pioneered by scientists at Caltech, including Ari Haagenschmidt, who was a Dutch chemist who moved to Caltech in the 1930s, I believe. And he was a flavor chemist who got sidetracked into studying the reasons why his plants were not behaving very well. And so in the process, he discovered the chemical reasons behind photochemical smog. And the main reactions are listed here. OH is a free radical oxidant in the atmosphere that does a large fraction of the transformations that go on, particularly with hydrocarbons, because hydroxyl radical is very reactive. It really wants to form water by taking a hydrogen from some other molecule, or by adding to, say, a carbon-carbon double bond. And so when that happens, in the presence of oxygen, you form RO2 molecules, which are peroxy radicals. These radicals are not as reactive as OH, but they're still fairly reactive. Their lifetime in the atmosphere is usually less than a few hundred seconds before they react with something else. One of the main loss processes, particularly where there's a lot of nitrogen oxides, is reaction with nitric oxide. This reaction is very fast. It forms NO2 and fragmentation products from the organic part of the RO2 that's reacting with the NO. In the atmosphere, under sunlight conditions, the NO2 photolyzes rapidly and generates an oxygen atom, which recombines with an oxygen molecule and forms ozone. So this is the main mechanism for ozone formation in the troposphere. And this cycle goes round and round as NO gets regenerated from photolysis, and you have this fuel input of hydrocarbon peroxy radicals. These cyclic reactions are terminated through when OH reacts with NO2 to form nitric acid, and when there's a small channel between the reaction of peroxy radicals and nitric oxide to form a stable molecule, which is we call organic nitrates. HO2 hydroperoxy radical is another free radical that can combine with RO2 to form hydroperoxides. And in the traditional understanding of how secondary organic aerosol was formed, it was through maybe several iterations of oxidation and functionalization of these organic backbones to the point where you have enough functionality where the vapor pressure lowers to the point where it can't stay in the gas phase, and it precipitates out on whatever surfaces are available, which are pre-existing aerosol surfaces for the most part. And that's how aerosol had been thought to grow. So are these, how important are these things for our health? Well, the World Health Organization and several other people or organizations have put a lot of thought and effort into this. And for the year 2017, it estimates that, you know, around 5 million premature deaths were caused by this air pollution, both indoors and outdoors. So that's substantial. I mean, that's number 4 on this list, right after high blood pressure, smoking, and high blood sugar, when you look at the global average. And this is, if you look at outdoor air pollution only, you drop to number 5 on the list. And on the right, I show a figure that shows how this has changed over time. You can see that the developing countries have the worst issues, but they're also improving their issues the most rapidly. The US has had moderate improvements over the last 30 years or so. Those improvements have been largely driven by regulations. And you can see that we're really good at regulating some things. This is a picture from satellite measurements of NO2 made by the OMI instrument in space. And you can see the annual column mean NO2 on the left and the column mean NO2 on the right between 2005 and 2013. And over this time, NO2 has dramatically decreased. So has that this regulation improved our air quality? Well, maybe in some places, but in other places, it seems like the improvements are not commensurate with, say, our reductions in NO2 in nitrogen oxides. And it could be that part of that is because the volatile organic carbon compounds, which are the fuel for this type of chemistry, haven't gone down at the same rate, but they have gone down some. But our improvements in ozone, so on the left, I'm showing ozone, the number of days where the South Coast Air Basin in Los Angeles exceeds the standard limit, which is 70 parts per billion for an 8-hour time period. And from the last 20 years, our improvement has only moderately improved, you know, by maybe 15%. And in the last few years, you might even make the argument that it's been getting worse. Particulate matter is a similar story. It was improving, you know, over the first 10 years of the 2000s, but then it's been pretty flat from there on out. And so that's something that we don't completely understand why this is the case. And so part of our work has been to try to understand why this might be happening and not improving, even though we're still decreasing nitrogen oxides dramatically. And so one question that we have is, or maybe there are other reactions for RO2 chemistry that we're not considering that are important. So we wrote a paper based on a few preliminary experiments that we'd done, mostly hypothesizing that autooxidation, gas phase autooxidation in the atmosphere is important in the general sense for atmospheric chemistry. This had not previously been recognized in any general fashion. Maybe for a couple specific species, it had been shown that autooxidation happens, but not generally. And so through a few experiments and a lot of calculations, we showed that this type of chemistry can be important even at temperatures that are relevant to the atmosphere. And this chemistry happens where you have a hydroxyl radical. It can abstract the hydrogen from, say, one of these CH2 groups and generate a peroxy radical. Now, this peroxy radical, instead of reacting with nitric oxide, can do an internal isomerization to make what we call a QOOH species, where it pulls a hydrogen from a CH bond and forms an alkyl radical. Now, in the atmosphere, where there's plenty of oxygen, this alkyl radical reacts with O2 to form another peroxy radical. And this process can happen now multiple times before you end up with a stable closed shell molecule. And if you add enough functionality, you can form a species that has a vapor pressure low enough to partition into the condensed phase or form SOA. So as this picture is quite powerful, as the wildfires have shown us, we live in an oxidizing atmosphere. It's quite clear, right? These fires in California are just terrible, but they show us that there's plenty of oxygen around, and if the conditions are right, we can really convert hydrocarbons into CO2 fairly ubiquitously and readily. And so it's perhaps not surprising that even in standard atmospheric chemistry, that this type of chemistry, this autooxidation, which is closely related to open burning, may be important. It's not a new idea. In fact, de Saussure, as the French chemist, discovered autooxidation in the early 1800s. This was only 25 years after molecular oxygen was discovered. So this is pretty remarkable for being able to at least understand part of what's going on, and this early in our understanding of chemistry. What he looked at was, say, alpha pinene in a closed system where he would put an oxygen atmosphere over the top. Well, he would hook it up to a balloon of oxygen, and he would measure the change in the volume of oxygen over time. And he found that over a few months that the oxygen was rapidly depleted, and in its place, CO2 was formed. And the case was somewhat different for, say, a different molecule, linoleic acid. The oxygen still disappeared, but you didn't make any CO2. And so this is what, at least from what I've researched and read, probably the first indication of autooxidation being discovered. Now, he didn't understand the mechanism. That didn't come for several years later. In fact, maybe 130 years later. H.N. Stevens was the person who discovered the key step in figuring out this autooxidation mechanism. He found, by studying the interactions of cyclohexene with oxygen, that this species, a hydroperoxide species, was the key intermediate in this autooxidation sequence. It was a fleeting intermediate also, because this thing is not that stable. It likes to transform into something else by breaking this susceptible peroxide bond. But over the next few years, the diligent work of many scientists just came up with this mechanism for how autooxidation works in the condensed phase. Basically, you form peroxy radicals from some initiator, which abstracts a hydrogen from an organic species. You add oxygen to form an RO2. That can react with another hydrocarbon to form a hydroperoxide and form another radical, which makes an RO2 radical. And this chain sequence can go round and round before it ends up terminating. And so that's how you can be very efficient at eating up this oxygen, even if you only have a small amount of initiator. Autooxidation has been recognized to be important in many other systems, including the rancidification of foods, like how butter can go rancid, even sitting in the refrigerator. Low temperature combustion, autoignition, where you get the engine knocking, is attributed to these RO2 H-shift isomerization reactions that form QOH. This is the reason why organic materials often have an inhibitor like hydroquinone added. This is considered to be an antioxidant, where this will quench this catalytic autooxidation cycle and form species that are no longer part of that cycle and stable. Also vitamins like vitamin C and vitamin E are antioxidants, which can interfere with these autooxidation mechanisms and bring the cycle to an end. Many biological species, including reactive oxygen species and processes, and the aging process have autooxidation invoked as part of that chemistry. But the question for us as atmospheric chemists, or me as an atmospheric chemist, is does gas phase autooxidation generally occur in the atmosphere? Well, it depends on the rates of these chemical reactions. That's really the key determinant in how important it is. An H-shift isomerization to a peroxy radical generally follows this type of energy curve, where the reactant must go through a transition state that has a significant barrier. These processes are generally thermal processes, so this barrier has to be accessible by the thermal energy that's available to these molecules. And so that limits the size of barriers that will lead to reactions that are important in the atmosphere. What these H-shift isomerizations have to compete with is generally reaction with nitric oxide, as we mentioned before, and with hydroperoxyl radical. Just ballpark values for the lower atmosphere in a region that's not, say, too urbanized would be NO being about 150 ppt and HO2 being about 30 ppt. If you take that along with these rate constants that are known, you get a typical lifetime of about 20 seconds. And so then you can go back and think about what this energy barrier actually has to be in order for these reactions to be able to compete. And it ends up being, somewhere around 20 kcals per mole is the, 18 to 20 kcals per mole are the barriers that can be overcome on this type of a time scale using thermal energies. So as we learned in organic chemistry, this type of a cyclic transition state, it really depends on the number of atoms in the ring. So this is ab initio calculations that show how the barrier height changes as you change the size of the ring. And so these idea that we were taught in organic chemistry really is true, right? When you have a 6-membered transition state, that is an ideal minimum for this type of isomerization reaction due to the low ring strain, and that tends to minimize the barrier. Also, the 7-membered ring, which is labeled here as a 1,6H shift, is in similar energy. But when you vary outside of those numbers of rings, numbers of atoms in the transition state, then you increase the energy to significantly higher energy, and those become much less probable as occurring. So can this be important in gas phase chemistry? Well, we need to know what these H-shift rates are in order to answer that question. Challenges to knowing what these H-shifts are the methods for detection of these oxygenated volatile compounds. There's not a lot of good methods to do that when you have, say, 4 different functionality groups on the molecule. Gas chromatography becomes very challenging when you have species like that. Secondly, the H-shift rates for RO2 are quite slow, and so it's hard to come up with an experiment where these processes can be measured. A flow tube often limits you to timescales of a few seconds, whereas we need to go to timescales of maybe 120 seconds. The diffusion path for over 120 seconds is quite large, so you're now talking about a flow tube that might be 1 meter in diameter to be able to study this process without wall interactions. Also, H-shift pathways, there's many possible H-shift pathways for at least larger molecules, and often the products have the same mass, and so figuring out which product corresponds to which reaction is complicated. But we've developed some instrumentation, a new tool, which allows us to measure some of these species. This is where we use a chemical ionization mass spectrometer coupled to a gas chromatograph system that uses a fairly short column, down to even a half a meter of a column, to get some of the more functionalized species through. And with the chemical ionization mass spectrometry. The chemical ionization mass spectrometer uses a CF3O- reagent ion to react with analytes to form cluster ions that are specific to the analytes. They preserve the parent mass of the analyte, either by attaching a CF3O- adduct or an F- adduct. So when you measure product ions, you can fairly readily determine what the actual mass of the analyte was. This, coupled with the chromatographic method, allows you to measure different isomers of the same species, and that ends up being very powerful for figuring out oxidative mechanisms. Here's just some examples from some isoprene chemistry. In fact, much of my time at Caltech has been spent studying isoprene chemistry. On the left-hand side, we show different isomers of the hydroxynitrates that are formed from the OH chemistry of isoprene in the presence of oxygen and NO. And you can see this is a very short column, a half a meter column, but we're still able to separate most of the isomers that are formed for the isoprene nitrates. And this has given us a wealth of information on how the isoprene photochemical cascades works in the atmosphere. Where there's no NOx, we form other products with isoprene, including the hydroperoxides. Hydroxy hydroperoxides are shown here in the first two peaks. And the peroxide goes through a very unique mechanism where it reacts with OH to form dihydroxy epoxides. So these two peaks here are a second generation product from this first generation product. And this data was actually collected in the field in northern Michigan from that profit tower. And you can see that these absolute amounts of material are fairly low, but we're still able to quantify them with reasonable precision. So now I would like to go through a couple of examples from the laboratory work that we've studied for specific auto-oxidation cases. Lu Zhu is a postdoc in our lab, and he wanted to study how alpha-pinene, the auto-oxidation mechanisms of alpha-pinene, and how important they might be for the atmosphere. And so you can see the reaction mechanism here. Alpha-pinene has a double bond which reacts readily with OH and O2 to form a peroxy radical. The peroxy radical can then react with NO to form hydroxynitrates. And shown here are two different isomers. When OH adds to this secondary olefinic carbon, this four-membered ring can open up to form this peroxy radical. And so, so what we do here is we monitor these specific isomers of the hydroxynitrates, and then we vary the bimolecular lifetime of the peroxy radical. Basically, how much NO do we have in the system? That's what we vary. And then we see if there's differences between the distribution of the hydroxynitrates over the function of NO concentration. And what Lu found is that one of the isomers, which is this tertiary nitrate from the ring open product, shows a big change depending on how much NO you have. When you go from NO that is, say, 500 ppb down to NO that is 5 ppb, most of this isomer disappears. And so what we attribute that disappearance to is an auto-oxidation mechanism, where instead of this peroxy radical reacting with NO, something else happens. And through different analytical methods and calculations, ab initio calculations, we figured out some of these processes. And one appears to be a ring closure, where this peroxy radical will interact with this double bond and form a covalent bond. And then you can add another oxygen atom to this. And then the other mechanism that can happen is the peroxy radical can extract these labile hydrogens that are allylic to the double bond. those end up being the weakest hydrogen-carbon bonds in the species. And for this particular species, the configuration is right? We're forming like a 6-membered ring or 7-membered ring. So this process is efficient and can happen under short times. Likewise, with beta-pinene, what Lou found was that this, again, the ring open nitrate product was the one that was responsive to changes in RO2 lifetime. At longer RO2 lifetimes, this isomer disappeared. And so from this data, we're able to extract what these autooxidation rates end up being. And so each one of these little points is a separate experiment that takes probably about a half a day. But you know, he persevered and collected a bunch of data and was able to get very nicely define what these unimolecular rate constants had to be. At room temperature, they're quite fast. They're 3 per second for alpha pinene and 13 per second for beta pinene. And so those we've shown here what the atmospheric levels of NO at 500 ppt and 5 ppb will be. 5 ppb of NO is a lot. I mean, that's as much as we get in LA during the daytime, maybe even more. I think the daytime average NO concentration in LA is probably now about a ppb. So these autooxidation mechanisms really will compete with the traditional bimolecular chemistry. A second experiment that I would like to talk about is Christian Moeller. He's a graduate student with some colleagues of ours at the University of Copenhagen in Denmark. He came to Caltech to do some experiments in our lab. He's usually a theoretical chemist who does ab initio calculations, but he wanted to try his hand at doing experimental work. And the system that he wanted to study was crotonaldehyde, as he had already done ab initio calculations on that, and that looked like a promising species to study. And so we use the same method here, where we're looking at the hydroxynitrate isomers as a function of time, as a function of RO2 lifetime, by varying the amount of nitric oxide in the system. And so what he found was really quite interesting. Crotonaldehyde, when you add OH and O2 to it, form, go to the next slide, form proxy radicals that have 2 stereocenters. And so as you know from organic chemistry, when you have 2 stereocenters, you can form the 2 diastereomers from that species. They're still very similar species, but these diastereomers end up, they are different, right? They have different physical properties. And that bears out especially in these H-shift isomerization reactions that we see, where one of the diastereomers reacts more than 10 times faster via autooxidation, this H-shift chemistry, than the other diastereomer. This is a huge effect, which is really quite interesting, and something I don't think gas phase chemists had realized before, that you can have such discrimination between diastereomers in gas phase reactions. But this unimolecular chemistry is very sensitive to small changes in the molecular configuration, and that's how you can get such big changes. Okay, so here's his Christian's curves as a function of a bimolecular lifetime. This is basically high NO at this end and very low NO at this end. And so it's these, what it's plotted here is the ratio of the nitrate that isomerizes to a nitrate, another isomer of the nitrate that has really no isomerization. And so the inflection point of this curve is the equivalency point where we infer that half of the species is isomerizing and the other half is reacting with NO. So if you know the NO lifetime, then you infer the autooxidation lifetime. So we've done several other and So in isoprene, this ends up being a fairly important autooxidation mechanism where OH and O2 add to isoprene. Isoprene is an important biogenic emission. 500 teragrams per year of isoprene are emitted mostly by plants, trees, oak trees in particular, to the atmosphere. And so this is a species particularly is important for atmospheric chemistry. And what we've been able to measure is these isomerization rates for these peroxy radicals. And they're fairly short, right? They're 3 seconds for one of them and 10 times faster, 0.3 seconds for the other one. So in the atmosphere, much of these isomers will undergo isomerization. Also, methacrylin, this particular product from methacrylin can do a 1,5/8 shift. I told you before that 1,5/8 shifts were probably disfavored because of the steric hindrance of this 5-membered ring as opposed to a 6-membered ring. But in the case of aldehydes, that ends up being an exception. 5-membered rings for aldehydes is actually very fast, just as fast as, well, close to as fast as the 6-membered rings. And so methacrylin, the hydroxyperoxy radical, isomerizes at 2 seconds with a 2-second lifetime. The other isomer would be the 6-membered ring from methacrylin, and that appears to oxidize or auto-oxidize even faster, though we don't have much data on this one because it oxidizes so fast. We've studied some carbonyls, 3-pentanone. This species is fairly slow, right? The barrier to this H shift is quite high. But once you add, say, a functionality and you come around to do the second H shift, this is very fast. It happens in less than 10 seconds, 0.1 per second or faster. Alkanes can also do this chemistry. Especially when you have a functionality group. If you have no OH group here, this ends up being fairly slow and of minor or to no importance in the atmosphere. But once you have an OH group, which you can form, this is a high yield product from say NO chemistry of hexane, then this second shift can go pretty fast, fast enough to compete in many places in the atmosphere. And the 1,6 shift from this isomer as well is fairly fast with a auto-oxidation lifetime of about 20 seconds. And then a few more from methyl pentene, 24 seconds, 5 seconds, 0.3 seconds, 0.08 seconds. This beta-pinene is one of the fastest auto-oxidation mechanisms that we've studied. This basically anywhere in the atmosphere will win. There's not enough NO unless you're right in the plume of a power plant or a tailpipe to compete with this quickness for the H-shift chemistry. So are auto-oxidation reactions generally important in atmospheric chemistry? Here's some data so we have to say what's the bimolecular lifetime of RO2 in the atmosphere to answer this question. Here's some data from Pasadena in the summer of 2017. And so here HO2 chemistry is really not important since NO is fairly high. You know, it's about a ppb in the afternoon, but you can see if you convert that into RO2 lifetime with respect to NO, during the daytime, you get to levels that are, 1 to 5 seconds. And so you can compare those with the numbers that we just went through in the table. And there's a number of auto-oxidation mechanisms that are going to win out. And this is in the middle of one of the most polluted cities in the country. So once you get away from the city, these processes will be even more important. So we say yes. Here's a review paper that came out last year, which is really quite interesting and shows that you can make some really exotic products doing this auto-oxidation chemistry. how about this guy, which is a product from, say, terpene autooxidation, where you can put on 4 different hydroperoxy groups on the same carbon backbone. This thing is really going to the particle phase immediately, and probably its lifetime will be very short given the lability of those hydroperoxy groups. So back to this, this slide, we would say that RO2 H shift chemistry is important for gas phase atmospheric chemistry and for secondary organic aerosol production. And so we really need to consider the various places that this type of chemistry can happen. And as atmospheric chemists as a collective, we're just starting to do that. So the overall impact on SOA has yet to be more fully elucidated, but I expect it'll be substantial most everywhere. Oh, so aging, autooxidation. I don't know, I'm still thinking about that. And then I will leave it on this acknowledgements page, and I'll be happy to entertain any questions that you guys have.
Okay, we want to thank John. So before we entertain questions, I forgot to mention that it was actually Jacob's idea to invite John Crounse. And that highlights something that I've tried to indicate to everyone, faculty and students, that we are always open to your suggestions. This was a really good, very excellent seminar that Aaron was inspired to request, and so that's something we'd like to have continue. I'm going to, I don't see any questions yet in the chat, so you guys could start putting your questions in. I have several questions. One is, where does, because in a lot of your lecture, you talked about NO. Where does NO come from?
Okay, yeah, sorry, I wasn't clear on that. In the, let me go back here. Go back to this main slide. Oops. In the atmosphere, NO comes from several places, but one important source is from industry and from combustion sources like automobiles, trucks. Trucks end up being the major mobile source for NO, given that how well catalytic converters work these days. So diesel combustion is the main mobile source for NO. That and chemical refineries and other combustion sources like that, high temperature combustion sources generate NO. There's also natural sources of NO from soil chemistry that are important in regions outside of the urban areas. But in the urban areas, it's all the diesel traffic that generates the NOx.
So that gets caught up in the evaporation and convection and goes into the upper atmosphere and does a lot of chemistry there.
Yeah, the lifetime of NOx. So you can think of NO and NO2. You remember the satellite slide I showed of NO2, right? So this change is all due to anthropogenic regulations on anthropogenic emissions, this giant change that we've seen. So you can get a feeling for the magnitude of the anthropogenic dominance for NOx in the atmosphere, at least over the continental regions. The lifetime of NO2 or NOx tends to be about a day or two in the atmosphere before it gets reacted away. Mostly, well, by OH is a major loss pathway. OH plus nitric acid plus NO2 forms nitric acid.
Mm-hmm.
The NO2 and the NO are in rapid photostationary state when the sun is out. So you can think of these as a single species for the most part.
Okay. So I have a follow-up question. I see Dr. Novak has one, Daniel has one. Let me just do the follow-up. Is it a true statement that the acid rain problem is fixed, because I think it's connected to the NO, right? Is that a solved problem, or is it like based on different regions within the US and of course then on a global scale? What's your?
Yeah, so acid rain was really problematic back in the 60s, 70s, maybe even the 80s.
Mhm.
Most of the issue, I think, was from sulfur for the acid rain issue. The nitrogen can cause acid rain,
Mhm.
but you need really high levels of it because the form that the nitrogen takes in the particulate phase is usually ammonium nitrate, which is pretty volatile for ground level temperatures. So most of the nitrogen doesn't stay in the particle unless there's really large amounts of nitric acid or ammonia around, like in the cow patty. But sulfur is a different story. When you oxidize SO2, which used to come mostly from industrial processes, coal burning was a large source of SO2, as well as refining, metal refining. You make sulfuric acid. And sulfuric acid reacts with ammonia, but that is much more thermally stable. So you can heat that up to very warm temperatures and that'll still stay in the particle because the ammonium sulfate is so much less volatile. And so that's what was driving most of the acidity in the rain and really causing damage to the biogenic material on the surface. But since we've regulated how much sulfur can be in coal, that problem has been largely regulated out. So it's not nearly the same problem it used to be. But in some places of the globe, particularly maybe China, sulfur is still a problem. Yeah.
Okay. So David, Dr. Novak, could you unmute and ask your question?
Sure. So the transition, as you say, from high sulfur coal to low sulfur coal has made a difference. I mean, do you see additional changes with the move to natural gas-fired electric power plants in terms of the composition of the reactive species in the atmosphere?
Yes, natural gas plants are much cleaner than coal plants. In the atmospheric community, we mostly think of the clean coal as a dream, a pipe dream, because it's just not that clean. It can be cleaner, but it's not that clean. Whereas natural gas, combustion is very efficient in these generators, these modern day generators. So you really end up emitting mostly CO2 from those plants. So they're much cleaner. I will say, however, that with much higher natural gas usage nowadays that we get from fracking, we end up leaking more carbon to the atmosphere than we used to. These fracking wells tend to be leaky, and so the methane emissions and other light hydrocarbons that come from these wells are more abundant now than they were before fracking.
Okay.
We'll go to student Lizzie, unmute and ask your question. Lizzie Borton.
Hi, yeah, I was just wondering if there's a way to clean the atmosphere after it's already been polluted, or if we can only limit the emissions that we put out.
Oh, that's a great question. So it really depends on what the particular species is. Some species, like these hydrocarbons that I talked about, are fairly reactive, with the exception of methane and ethane, which are the two perhaps simplest hydrocarbons. The lifetimes of these species is pretty short. It's a week or 2 weeks before they get converted into other species, which are even more reactive and basically get either lost to deposition or rain out, or converted to CO2. CO2, however, is a very long-lived atmospheric gas. Its limitation is fundamentally limited by weathering of silicate materials. And that process is very long, right? It's maybe 1,000 years for the lifetime of CO2 by that process. There's a shorter term sink, which is depositing CO2 into the ocean, but the ocean is a reversible process, right? So if you deposit a bunch of CO2 into the ocean and then you drop atmospheric levels of CO2, now the CO2 is going to come back out of the ocean. And so you're not really getting rid of it, unless it gets into the deep ocean where the mixing time scale is very long.
Okay. Let's get JP, Joshua Park.
Hi, I was wondering what alternative energy sources you find the best in large scale implementation, or like what we could move toward in the future.
Oh, yes. I think alternative energies are very good across the board for the most part. Solar is really coming on strongly now, at least on the West Coast and in California. We have solar on top of our house that supplies basically all of our energy needs. I think California now has 20 or 25% solar. It's reached the point where in the middle of the day, electricity costs, wholesale electricity costs are basically zero. And it's because of all of this solar energy that's abundant. And so what we really need to make use of this is to get a better storage system for solar. Wind power is also good in certain areas. It could be that there are some problems, right? What's that? Oh, it could be that there's some problems with killing wildlife and things like that. But people are working on ways to have birds avoid the windmills. They also, though, take up space, right? You don't want to live in the middle of a windfield, windmill windfield.
Mm-hmm, mm-hmm. Okay. Nels, is that how you pronounce it? N-E-L-S, Nels or Nels?
It is.
Okay.
So are there any plans in place to actively reduce the contamination in the atmosphere, or is most work currently focused on reducing the rate of pollution and contamination?
I will answer this with respect to CO2, which is that long-lived gas, and an important greenhouse gas, right? It acts like a blanket over our planet and causes the equilibrium temperature to be warmer than it would be otherwise. There are active implementations for trying to remove CO2 from the atmosphere. People are actually trying to remove it from the air and then put it deep into the ground, either under the ocean or in deep wells that used to be used for getting oil and fossil fuels out of the ground. If you put CO2 down deep enough, the pressure is high enough that it is a liquid and it'll stay down there. And so that's something that is being done actively, though the scale at which it's currently being done is nowhere close to the scale that it's currently being emitted. So we'll have to see if that's feasible to do in the long run.
Right, right. Aaron, your turn.
Yeah, so actually it's about the slide you're on right now. So for the NOx species, it's decreased in a lot of these areas over the Midwest and East Coast significantly, so it looks like half to maybe even a third. But that is, compared to like Wyoming or Montana, these places that are pretty remote, which presumably have very little emissions there. They're like in the 0.1 to 0.5, molecules per centimeter squared. So it's, that our emissions are still, 10 to 20 fold higher maybe than they naturally would be. Does that, even though it's better, it's still not great. Does that contribute to the next slide? We saw the charts. Right there. Like the PM or any of these statistics, is that the pollutants, even though I don't know if there's any connection there. I don't if I missed that.
Yeah, no, that's a good question, right? We're still in the places where a lot of people live, really perturbing the NOx levels in the atmosphere. And you know, that will take some time. They're going down, they're still going down. That data was 2013. In 2020, it's probably gone down by another factor of 2 or so from then. And we expect that it'll probably keep going down. And possibly when we reach the point where most of the vehicles are electric, you know, it'll be substantially lower. Now, whether it'll be background levels, it's probably never going to reach background levels because there will always be some combustion sources. But the NOx chemistry is very nonlinear in terms of how much ozone gets produced. When you have a lot of NOx, it actually limits how much ozone gets produced because you react all of the oxidant with the NOx and you form nitric acid, and that basically kills the chemistry. Now, as you reduce NOx to lower levels, you end up making the ozone production more efficient because you're not sucking away as many of the oxidants. And so you'll reach a point where you actually hit a maximum in ozone production as you reduce NOx away. And so you have to get over that hump and get on the other side before you're going to start seeing beneficial increases in ozone. The other way to look at this problem is from the VOC side, right? I didn't talk much about VOCs, but they have not gone down quite as slowly as the NOx level. And so you could start putting more controls on the VOC, which are the fuels that make this ozone, and that would be helpful. Now, the particulate matter is a different story, and that's what I talk most about. And if the auto-oxidation ideas are really right, as we decrease NOx, we'll think that we're going to potentially get worse in how much particulate matter there is, though that's yet to be seen. That's basically just my hypothesis. The thing that's happening at the same time is as you decrease NOx, you also change the oxidant levels. And the oxidant levels behave much like the ozone levels. You're gonna, as you decrease NOx, oxidant levels will increase for a while till you get to a point. And then when we get over this hill, the oxidant levels are gonna decrease. And when the oxidant levels decrease, that'll slow down photochemistry in general. And so as my advisor at LECO used to say, pollution is the solution to dilution is the solution to pollution. So if you can slow down the chemistry enough, right, then these problems will become much less.
Mm-hmm. So Dara, you got a good question, a different question here.
So I know you showed us the plane from NASA. Like, is there a difference between getting a sample directly, or is it just the same as getting a sample and then analyzing it on the ground?
Oh, that's a good question. Yes, well, it depends what you're trying to measure. So our instrument, I didn't talk about really what we measure from the plane, but we measure hydrogen peroxide, nitric acid, formic acid, acetic acid, hydrogen cyanide, a number of different trace gases that are usually present at say a few parts per trillion to a few hundred parts per trillion, maybe a part per billion for the case of hydrogen peroxide. These species are pretty labile, and they don't really like being, say, put in a flask or a container of sorts, because they end up interacting with the surfaces of the container and they get lost pretty easily. So the measurements that we make with this instrument in real time are directly while we're flying. We sample air from outside the aircraft at a very high rate of flow to these mass spectrometers, and in that way we can minimize the losses on the surfaces and get a reasonably good measurement of what's actually in the air. If you were to try to put most of these species into a canister, they would go away, within a few minutes probably. you can't see it here, but right on the other side of the aisle from us, there's 3 racks that are filled up with 2-liter stainless steel cans. And that's called the whole air measurement. And they do just what you were describing, where they will vacuum out the can from all of its contents. And then while the plane is flying, they will open a can one by one and fill it with air from different regions where the plane flies. And then they take those cans back to the lab, and they're able to do more complex analysis on them, but they're only able to get data for things that survive in the can. So that would be more long-lived species like small hydrocarbons and say fluorochlorocarbons and things that are stable in canisters. So yes, on the airplane, there's both kinds of measurements, and it really depends on what you're trying to measure, which decides what type of instrument you need to use.
Okay. Maybe a couple more. I was thinking Nick has one about the impact on humans. Nick? Is Nick there? If he isn't, I'll ask it for him. So you talked about some of the negative impacts of particulate matter can have on us. Are certain groups of people more vulnerable to these effects than others, such as old versus young, smokers versus non?
I'm not sure. I'll give my opinion. I'm not an expert in these health effects by any means. Probably some of you guys know more than me about that, but I would venture an answer that is probably so. You know, if the lung already has some damage, which may be the case in people that have asthma or COPD or something like this, then exacerbation of those already damaged parts can be more impacted by, say, the ROS that comes with particulate matter. So yeah, that's my opinion.
Okay, so for the last question, I would say whoever wants to ask a question, whoever goes first, that would be the last question. Anybody who wants to ask a question? You guys are not really fast in the draw. I have questions too still. So I'll close with one question. Then, so with all these wildfires happening now, are you aware of a lot of atmospheric studies being done to, you know, monitor the different types of gases, their concentration, their transport, and so on through the air? I'm assuming there is, but is there? Are there?
Yes, there are. In fact, we were part of one of the aircraft missions on this plane right here, the DC-8, that was last summer. It flew out of Boise, Idaho, and also Salina, Kansas, specifically studying the emissions from fires in Boise. From Boise, we looked at wildfires in Montana and Wyoming and Idaho and even Arizona, 1 or 2, and California. And then out of Salina, Kansas, we were looking mostly at agricultural burning. And the year before that, I think NOAA, the National Oceanic and Atmospheric Administration, had a specific scientific mission called WECAN that looked at fires also in Boise and the Northwest sector. So it certainly is a important research topic right now. In fact, I happen to be a co-author on a biomass burning paper, and it's the most cited paper that I have. Even though that's not really the focus of my work, but we are interested in those things, and we do try to study them. Especially in the last few years, the interest in biomass burning is really increasing, and it's for good reason, right? Because huge amounts of material is going up, and more each year.
Right. So maybe we could bring you back in maybe a couple of years, talk about the biomass and see.
Sure. Yeah. Yeah. That would be fun.
All right. Well, again, we want to thank you very much, John, our alumni that we are very proud of here, for taking some time out to talk to students here, faculty and staff. We appreciate what you've accomplished, and we are thankful for the time you spent with us.
Thank you. I really enjoyed seeing everyone and giving this presentation. That was a lot of fun.
All right. Thanks.
Thanks, guys.
Okay, take care.
Okay, we'll see you guys later.
All right, bye-bye.
Bye.